Welcome to this video lecture. This is Mark Scythian, FAA licensed aerospace technician, airframe power plant and avionics certified. The date today is April 15, 2017. The title of this lecture is Accurate Two-Blade Propeller Thrust Calculation. Propeller aerodynamic equations are by far among the most complex computations in the fields of mechanical and aerospace engineering, aviation technology, and fluid dynamics. An aerodynamic propeller is essentially a rotating wing or airfoil in which the coefficient of lift is kept constant across the blade span. The airflow speed which flows over a rotating wing or propeller is a function of the circumference. This is because at the blade root of a propeller, the circumference pathway is much shorter than the circumference pathway at the blade tip. Circumference is a function of the diameter, and larger the diameter, then longer the inner, middle, and outer circumference pathways are. See the illustration on the next page. Here's a drawing that I put together representing this model. At the blade root, you have a shorter circumference pathway compared to the midsections in the tip. This means that even though the RPM will be constant across the entire span, the airflow speed will be much greater at the tips compared to the roots. So therefore, the rotating airfoil angle of attack at the root will be much greater to compensate for that lower airflow speed. And of course you have a broader root because you don't want to have too short of a chord with high angle of attack. And then as the blade projects outward, you see that the angle of attack decreases, and this creates a helical twist going from root to tip to keep the coefficient of lift constant upon the blade airfoil structure. So both Newtonian and Bernoulli force components are applicable just like with a fixed wing airplane wing. It's just that you have a helical twist to distribute the amount of lift / thrust across the blade span. A rotating wing, propeller, or helicopter main rotor permits aerodynamic thrust or lift by rotation, where a linear wing or fixed wing airplane on an airplane permits aerodynamic lift by linear forward motion. The only difference between the two is that with propellers, the airflow speed over the rotating airfoil or blade decreases from blade tip to blade root. This is because the circumference of the blade tip is much greater than the circumference of the blade root. In order to keep the coefficient of lift across the rotating propeller blade relatively constant due to the airflow speed differences from blade root to blade tip, is to establish a helical twist from higher blade angle to lower blade angle starting from the blade root to the blade tip. Coefficient of lift in regards to rotating propellers translates into the coefficient of propeller thrust. An aerodynamic propeller is nothing more than a rotating wing airfoil subject to the same Bernoulli and Newtonian force components that an airplane wing or a fixed wing is also subject to. But however, the dynamics become extremely complex in regards to propellers as the airflow speed across the propeller blades instantly change at different positions across the propeller blade. A series of interlocking airfoil structures with high AOA or angle of attack at the root decreasing the low angle of attack at the blade tip must carry on without compromising structural integrity while averting airflow separation from the blade surfaces. This not only includes static thrust conditions but also dynamic or net thrust conditions when oncoming airflow merges into the propeller arc airflow into what is known as geometrical pitch. Just as airplane wings can stall due to flow separation, especially at excessive positive angle of attack, under flight speed conditions, deep stalls, and airfoil profile irregularities such as damage or ice buildup, a propeller's blades can be in rotation while airflow separation is also occurring. This is also known as propeller stall. Operating at too high a blade pitch at low flight speeds, ice buildup and damage to propeller blade airfoils are usually the cause of propeller stall and failure. Higher blade pitch requires higher flight speeds and also permits higher flight speeds as well. Lower blade pitch is used at takeoff and climb conditions at lower flight speeds. Blade pitch is defined as the amount of airflow displacement the propeller will displace per one revolution, usually rated in inches pitch. On the other hand, a single so-called blade angle value is not relevant since there are so many different blade angles from blade root to blade tip. The blade angle may be as high as 45 degrees at the root, 25 degrees at the blade midsection, and 5 degrees at the propeller blade tip. But the overall quote-unquote blade angle is referred to as helical twist, which is typically between 8 to 10 degrees on many propeller designs, representing the overall helical twist across the entire blade from root to tip. The relevant data for understanding propeller performance capabilities are blade diameter and blade pitch. A typical propeller specification would be something like 60 by 22. The 60 refers to the inches diameter and the 22 refers to the inches of airflow the propeller will displace or accelerate per one revolution of the propeller. Always remember that propellers are rated by inches diameter and inches pitch. The differential equations regarding aerodynamic propellers are very complex and include statics and dynamics, integration of aerodynamics, strength of materials, manufacturing, mechanical power transfer, centrifugal force, aerodynamic stresses, coefficient of lift, coefficient of drag, bending stresses, dynamic pressure, helical blade twist, blade pitch, acoustics, harmonics, hyperflows, disc loading, and propeller efficiency regarding the structure. And then when put onto an airframe, then the torque, rigidness in space, and gyroscopic precession must all equally reach an equilibrium throughout the rated RPM operations for the given power plant's brake horsepower, torque, and mean effective takeoff horsepower for the given airframe. So there's a lot going on here, and I just, instead of saying that, I wanted to give some of the details of what goes on with the propellers, especially on their design. So it is a whole separate science, propeller design is. Many different manufacturers of propellers also have their own algorithms, computational fluid dynamics, CFD, and finite elemental analysis, FEA, including propeller thrust formulation based on air temperature, coefficient of flow, propeller efficiency, and various industry standards. It becomes somewhat frustrating for innovators, technical developers, technicians, and designers to implement a certain industry standard of propeller thrust formulation to their own projects or perhaps their customers who desire a certain propeller performance output. Manufacturer certified software, IT consultants, and aerospace engineering consultants are usually outsourced in order to calculate propeller thrust computation for propeller design goals. Creating, deriving, finding, or relying on a highly accurate two-blade propeller thrust equation applicable to all two-blade propeller applications isn't exactly easy. The simplified momentum theory is also an option for calculating propeller thrust, but isn't consistently reliable for accuracy's sakes. Also, experimentally bench testing propeller performance to make adjustments is also a basic option as well. But when such an accurate and reliable propeller thrust equation is found and rigorously verified with software, practical applications, experimentation, and real-world testing, it is certainly worth sharing with those in the mechanical and aerospace technology community and or other related technical fields. Recently, I discovered the aerodynamics research platform of a person named Gabriel Staples at the following URL website link. I don't have a hyperlink on this video, so you might want to just copy that down and visit that site sometime. Gabriel Staples published a propeller thrust equation that is 90% accurate to actual two-blade propeller thrust testing of nearly every manufacturer and make of propeller. This includes propeller applications in all practical air temperature and elevations above sea level ranges, which is quite remarkable to say the least. Most of the time, developers, technicians, designers, and inventors will experimentally bench test a propeller and record the static thrust output, RPM, brake horsepower, torque, and pitch to determine the true performance capabilities of a given propeller, including propeller discharge, airflow speeds, and maximum flight speed limitations. Again, the relevant specifications to look for when working with propellers are pitch, diameter, RPM, forward speed, propeller discharge velocity, and an industry propeller efficiency standard of 80%. The purpose of this lecture is to share a propeller thrust equation which is very accurate to actual propeller thrust values when experimentally tested. This equation is reserved only for two-blade propellers only. Here is the two-blade propeller thrust equation courtesy of Gabriel Staples. You would use this, the F represents the force thrust in newtons, would be equal to this constant times the RPM times the quantity of the inches diameter of the propeller to the 3.5 power divided into the square root of the inches pitch, then times this constant times the RPM times the pitch in inches in one quantity, and then subtract the forward speed if you want to get net thrust. But if you're dealing with static thrust, you just enter in 0 here. Example, calculate the static thrust of a fixed pitch propeller with the following specifications. We have a 2-blade fixed pitch propeller with specifications of 60 by 22, rotating at 2500 RPM. So we list this data down, and then we have 0 flight speed, so we're dealing with static thrust. So when we enter in all these values in the quantification and parentheses, we get a static thrust of 912 newtons. It's 4.45 newtons to 1 pound of force, so 205 pounds static thrust. And I've tested that experimentally and also with software, and it's about 95% accurate. Many other applications I've tested, and it's between 90 and 95% accurate consistently. And you notice that there's no component for propeller efficiency, because whatever Gabriel Staples did, he set up an equation derived that finds that middle ground between all efficiencies. So I was very impressed. Of course, you got to be skeptical at first, but when even software is equaling the mathematical calculation around 95% every time, it's like, wow, it's worth sharing. Because a lot of people are searching for a general equation, and it's not that easy to find. But what Gabriel Staples did was quite remarkable, so I thought I would share this. Now, if this 2-blade propeller was on an airplane flying at 130 miles per hour, calculate the propeller net thrust. So we got to convert 130 miles per hour to meters per second. So we calculate the feet per second conversion, and then we divide it by 3.28, number of feet to a meter. So 130 miles per hour is 58.14 meters per second. We enter it into the formula again, and this time instead of 0, we put 58.14 to represent V1. So 853.9 newtons net thrust divided by 4.45, 191.9. And I tested this also with software and also on some drone projects. Not this size, but other propellers that are fixed pitch, like 10 by 8 or something. It's very accurate. This equation for typical 2-blade propellers has an accuracy of approximately 90% or more. However, for more complicated multi-blade propellers such as fixed pitch 5-blade ducted fans, the accuracy in this case is around 85%. 3-blade propeller thrust calculations also resulted around 90% accuracy using this formula. What you can do is use this on a 2-blade application and then use a logarithm that you can look up for equivalent multi-blade propeller scaling. And then actually what I did is, of course, on the EDF lecture, you notice that getting the actual propeller thrust within the duct is a function of the mass airflow acceleration differential. And in that lecture, we calculated like 0.7. I use 0.7 pounds of thrust, additional propeller thrust, along with the Newtonian aerodynamic thrust out of the exhaust. And when I implemented this formula for a 5-blade fixed pitch ducted fan rotor, I got about 0.6. So 0.6 to 0.7 is 85%. However, if we go back and take that from a 2-blade 3.043 inch propeller fixed pitch with a 3-inch pitch, and then calculate the thrust, and then use that logarithmic equation for 5 blades at the same pitch, it comes to about 0.7, 0.68. So again, we're very, very accurate. 0.65, about 95%. So on the previous EDF lecture, you'd have to take actually the airflow rate change from the inlet to the intake, and that would be your acceleration that you're dealing with. And then, of course, you would take that to the mass of the air entering the disk area. And so 0.7 is what we got on the EDF lecture. I think it was part 3 or 4 when we were doing that equation. So I tried the EDF 5-blade propeller fan at 42,800 RPM and 3.043 inch diameter, 3-inch pitch, and I got about 0.6. But when I did that with 2 blades on the same diameter pitch and then used the logarithmic multi-blade equivalency, I got about 0.68. So that's very accurate, even with logarithmic adjustments for multi-blade applications. Propeller static thrust mathematics are very complicated and limited to manufacturer's formulation and specifications per propeller design, more so than a general propeller thrust equation. However, the general equation that Gabriel Staples has derived is relatively accurate to real-world propeller thrust applications. I felt that making a lecture pertaining to this general propeller thrust equation was worthwhile to share. And again, that would be this formulation here, just for reference sakes again. If you use this, you will have a relatively accurate propeller thrust mathematical formulation to work with. Thanks for watching this video. Like and subscribe, and have a great day.